All right, how about that test? Woo, man, and that one question about that one thing. Whew, all right, well, time to move on. So we learned about applications in the last part, and now we're going to move on to techniques, the various techniques. And let's start with a little bit of review. So when we took derivatives, we learned three important rules. And first rule, the derivative of a sum is the sum of the derivatives, and also we can take out constants. The second one, derivative of f of g of x is f prime of g of x, g prime of x. This is called the chain rule. And the third one was the derivative of f of x times g of x is f prime of x times g of x plus f of x, g prime of x. And we've been learning about rules for integrals. So for instance, we have that the integral similarly breaks up over addition, can pull out constants. And we have one of our most powerful things that we've learned so far is what we call the substitution rule. Integral of f of g of x, g prime of x dx. Well, let's change our name. Changing names, very important thing to be able to do in mathematics. So we'll set u, a new variable, equal to g of x, and we have du is g prime of x dx. When we rewrite the integral, it becomes integral f as a function of u du, so it simplifies. So what we can think of is that we really are taking rules for derivatives and making rules for integrals. So for instance, this rule says that derivatives are linear. When we transform it over, it says, aha, integrals are linear. This rule, we have a nice name for derivatives. It's called the chain rule. Well, now we transformed it over, and we got the substitution rule. And this rule was the last one, the product rule. Well, what does it become? And that's what we're going to learn. It's called integration by parts. Today, let's fill in that box. Okay, so what's the idea? Well, it's fairly straightforward. What do? We start with the product rule. The derivative of f of x, g of x, is f prime of x, g of x, plus f of x, g prime of x. And now, take antiderivatives. You'll notice on the left, the antiderivative of the derivative, well, that's pretty straightforward. That's just a function again, f of x, g of x. And on the other side, we have the antiderivatives of the functions. Antiderivative of f prime times g plus the antiderivative of f times g prime. Well, rearranging, we get the following. And this is the product rule, becoming integration by parts. Integral f of x, g prime of x dx is f of x, g of x minus the integral f prime of x, g of x dx. So in particular, what did we do? We moved that to the other side. Now there's a couple of different ways you'll see this written, and a very common way is using u's and v's. So if I let u be f of x, so everywhere where I see f of x, I'm going to say that's u, and notice that f prime, I'll call that du. V is g of x, so everywhere I see a g of x, I'll put v, and dv will be g prime. Then I get the integral of u dv is uv minus the integral of v du. Okay, well, what's the point? Well, the point here is that we're changing. So instead of having an integral f times g prime, we have the integral f prime times g, which, if we do our job right, is easier. Now, the question is, how do we know if we're doing our job right? Well, practice. But really what we should be seeing is we should be seeing progress towards a simpler integral. In calculus, it's oftentimes several steps, reducing, simplifying. We're trying to get to something simple. Well, how do we know to make a good choice for u? Well, u, in the original part, that's u dv. We're going to differentiate that. Well, if we have something which is hard to integrate but has a nice derivative, that's a great choice for u. And in particular, if we're trying to integrate something which we've never integrated before, all right, that's u, no choice. Another good choice for you is saying, well, look, let's try something where if I keep taking the derivatives over and over again, eventually it vanishes. It simplifies really nicely. So for example, x to a power like x squared, x cubed, so forth and so on. Eventually it goes away. What's a good choice for v? Something that's easy to integrate. And sometimes maybe the integral is even simpler. It happens. Look for something which is stable. E to the x, sine x, and cosine x, essentially when you integrate those types of terms, they pretty much stay as they currently are. And so you can integrate, nothing changes, then what's happening is the other part, the u, you're differentiating, simplifying. Away it goes. All right. Well, okay, theory. Now let's talk practice. Okay, so let's try an example. Here's an example. Suppose we're asked to do the following. What's the integral of x, e to the x, dx? Well, let's think about it. We have two pieces, the x and the e to the x. So one of these is going to be our u, one of these is going to be our dv. Whether we differentiate or integrate e to the x, we're still going to get e to the x, so I really don't care what that is. And now I say, well, look, if I differentiate x, that's easier. If I integrate x, I get x squared. That's harder. So let's make this the part we differentiate. We'll call that u. We'll call that dv. So du will be 1 times dx, and v, the integral of e to the x, is e to the x. So we get that this is uv x e to the x minus the integral v du. Integral e to the x dx. Ah, fantastic. Easier. Easier. Woohoo! X e to the x minus e to the x, and then of course always plus c. Plus c. Good. All right, done. And that is integration by parts. And now let's do it 50 more times. And the more we do it, the easier it'll get, and it'll get quicker. Now, let's think about a slightly different example. Suppose I say, what's the integral of x e to the x squared? You're like, ah, perfect. I know. Same idea, right? Here's the u, and here's the dv, and I just keep going. Except, hold on, we can't integrate e to the x squared. Can we integrate this? Yeah, okay, so what we can do is we can do the following. Really what we'll think about this is, let's let u equal x squared. Du is 2x dx. All right. Or 1/2 du is x dx. And so what I can do is that this integral becomes the integral of 1/2 e to the u du, which is 1/2 e to the u plus c. And so we get our final answer, 1/2 e to the x squared plus c. That's our answer. Okay, what's the point? What's the point? Well, the point is, look, just because we have this new tool, integration by parts, doesn't mean we should stop using our old tools. In fact, we need to put priorities. Priorities. Substitution always should be a top priority. So substitution before the product rule, or subs before prods. I don't know what that. Okay. Anyways, the point here is look for substitution first, and then no good substitution. Then think product rule. Product rule. Okay. All right. Next, let's try another one. Let's think of the integral of log x dx. And now you're thinking, okay, two things. One, I don't know how to integrate log x, so it'll be nice to finally find out how to do it. And two, we're supposed to be learning about integration by parts, which says there should be a product. And I don't see two things multiplied. Well, the thing is, there's always that hidden 1. So if you don't see two things, just say, well, look, it's like 1 times something. Now, in this case, we have the log. We don't know how to integrate. We have to differentiate. So we're not given a choice. U has to be log, which means that dv is 1. So du will be 1 over x, and v will simply be x. And so now, what do we get? Well, we'll get u times v, x log x, minus the integral v du, x times 1 over x dx. Or, cleaning this up, x log x minus the integral of simply 1. Ah, that's one of our favorites. X log x minus x plus c. There we go. Of course, we can check. You know, we might be skeptical. Is this right? If you do this, what you'll see is you take the derivative of x log x, you use product rule. Okay, integration by parts comes from the product rule, so that's very natural to use that. You'd have, if I took the derivative, it would be the first times the derivative of the second minus, or rather plus, the derivative of the first times the second. And then I have to subtract the the derivative of x, subtract 1. And you'll see that x times 1 over x cancels with 1. So the derivative is log x, which checks out. So we definitely succeeded. That's a good smile. Success. Success. So far we've talked about doing integration with antiderivatives. We can also do definite integrals. So suppose we want to do the following. We want to find the integral from a to b u dv. Well, it is uv evaluated from a to b minus the integral from a to b v du. Why? Well, we just go back to our product rule and we integrate both sides from a to b, and the result pops out. Easy, easy. Okay. So let's do one of my favorite functions. You knew it was coming. It had to be here. Arctangent x. What is the integral from 0 to 1 arctangent x? Well, we don't know the integral yet. Today is the day. Let's find it out. Okay, again, it's like the log. So what we're going to do is put a 1. We're going to let u equal arctangent, and then we're going to let dv be 1. So that du, derivative of arctangent, is, right, 1 over 1 plus x squared. And v, integral of 1, right, x. Okay, good. So this is going to be u times v, x arctangent x from 0 to 1 minus the integral of v du, x over 1 plus x squared dx, and integrating from 0 to 1. Now, we can evaluate here. If I plug in x equals 1, I get 1 times arctangent of 1, which is pi fourths, subtract 0. So I'm going to get a pi fourths. Now here, for the second integral, now there's no more arctangent, so we can use anything we want. Anything. Well, here's something. We can do a substitution. So let's do a substitution. We'll let u equal 1 plus x squared. Du is 2x dx. Or 1/2 du is x dx. So I get that this piece would be minus 1/2 integral, plug in my bounds. They used to be 0 to 1. They'll now become 1 to 2. So 1 to 2. And then that 1/2 came from the 1/2 du, so it's du over u. So that's minus 1/2 log u from 1 to 2, which is minus 1/2 log 2, and then minus minus plus 1/2 log 1. Okay, log 1, 0, gone. So the second part here with the minus is minus half log 2. Combine it with the first part, we get that our final answer is pi fourths minus 1/2 log 2. Done. All right, good. Now, what's next? Well, let's try something a little bit interesting. Suppose I ask the following. What is the integral of sine x, cosine x, dx? Now, I think we could actually integrate this without doing integration by parts. For instance, we could do substitution, and we'd get the answer. What if we did integration by parts? We could do it a couple different ways. And so let's try the following. I'm going to call this part my u, and cosine x dx, that's my dv. So that du will be cosine, and then v, integral of cosine, well, that's positive sine. All right. So I get this is u times v, which is sine squared x, minus v du. So minus the integral of, and I'll put the sine x cosine x dx. Okay, well, interesting. Let's try something a little different this time. Now, this time, let's try to make cosine x, let's make the cosine x u, the sine x dv. So in other words, u, cosine x du, is negative sine. What's the integral of sine? Well, the integral of sine is negative cosine. Okay. So let's be careful here. This is the part where people oftentimes make mistakes, is when you apply integration by parts multiple times, you have to remember that minus. So sine squared x minus. Okay, I'm going to put parentheses there so I don't get confused. I'm going to have u times v. So that's minus cosine x times cosine x is minus cosine squared x. And then minus the integral of v du. So minus cosine x, oops, I forgot my dx here, minus sine x dx. All right, so now that we have that, we are almost ready to go. Let's clean this up. Okay, let's be careful here. This becomes sine squared x plus cosine squared x, and minus minus here. Two minuses make a plus. And notice another minus minus. So that's another plus, plus integral sine of x cosine x dx. Okay, wait a second. That's what we started with here. Okay, let's cancel. So if we cancel, we get 0 equals sine squared x plus cosine squared x. All right, cool. And from trig, we know sine squared plus cosine squared is equal to 1. 0 equals 1. Cool. Wait, what? No, this means my life has been a lie. If 0 equals 1, math is just no longer true. Okay, all right, wait. Something had to happen here. Something had to happen. Where was our mistake? There had to be a mistake, because in fact, I will tell you, the truth is that 0 does not equal 1. And 0 does not equal sine squared plus cosine squared. Okay, so if there was a mistake, where was the mistake? Now this is a little bit subtle, but let's take some time and think about it. And I'll point it out. The integration by parts was fine. No problem. The mistake here was we said, look, this part, integral of sine x cosine x dx, and this part are the same. So we can cancel. But in fact, they're not the same. Which is really weird because they literally have the same expression. Well, what do I mean by they're not the same? I mean the following. When we write down an integral, remember that there's a built-in plus c. So that this is some integral, antiderivative plus c. This is also an antiderivative plus some other c. These constants don't have to be the same. So they don't actually cancel. What is true is that when you cross these out, you don't get 0, you get some constant. So that we can conclude that sine squared plus cosine squared is equal to a constant, and that is true. So this is a little side note, something that you can stump your friends with and ask, where did we make our mistake? Okay, so let's go on. Now, one of the things that you saw with that last example, other than it's quite silly, is that we have to sometimes do integration by parts multiple times. And if we do that, we can get a nice answer. So here's an example. Suppose we're asked to integrate x cubed sine of x dx. Now our philosophy says, look, sine of x, integrate, differentiate, it still looks pretty much like sine x. X cubed, well, when we differentiate it, 3x squared. Okay, that's a little smaller power. Differentiate that, x would be 6x. Differentiate that, 6. Differentiate that, 0. So differentiating x cubed, it's sort of grinding away, wearing it down until it finally says, okay, fine, I'm out of here. So here, an ideal substitution to make is to say, let's let that part be u, let's let that part be dv. du is 3x squared dx, and v, antiderivative of sine, is negative cosine. So we get u times v, negative x cubed cosine of x, minus the integral v du. Now notice that there's a minus here. So minus minus, I can make this plus the integral of 3x squared cosine x dx. Now what? Well, we repeat. Let's make now this part u, and we'll make this part dv. du is 6x dx. v, antiderivative of cosine, is sine. So we now have minus x cubed cosine x still is there. It's being added, so that's nice, plus our u v term, 3x squared sine of x, minus v du. So the integral 6x sine of x dx. Okay, we're making progress. We had an x cubed, had an x squared, now we're down to an x. One more time, and that should do it. Let's let this be u. This can be our dv. Then du will become 6. And v, well, that's the integral of sine. Integral of sine is something we already did. That's negative cosine. I guess I should put 6 dx here to be consistent. Okay, so we have minus x cubed cosine of x plus 3x squared sine of x minus, and I'm going to be careful here, this minus, I cannot warn you enough. This is what throws a lot of people off. So I'm going to put parenthesis so I remember to multiply it through correctly. 6x times negative cosine x. So minus 6x cosine x minus integral v du. So that'll be minus the integral. Of course, the minus minus makes plus. And then I'm going to have 6 cosine of x dx. And now let's go through and let's finish this up. Negative x cubed cosine x plus 3x squared sine of x. Here we go. Minus minus makes plus 6x cosine x. Okay, now the integral of cosine is sine. So this part right here is 6 sine of x and minus that. So minus 6 sine of x, and finally plus c, plus c. All right, always remember your constants. Okay, so you can see the philosophy here. It's just we have that x cubed and we're just chipping away, and eventually we get to the point where, look, there's no more x, and now it's a straightforward integral. All right, well, what happens when we have something where we have integration by parts and we do it and we get stuck in what feels like a cycle? So let's try such a problem. So for instance, suppose we have the following. We have the integral of e raised to the power ax and cosine of bx dx. Now, these functions are really quite nice functions. And by quite nice, I mean if I integrate e to the x, I essentially get e to the x. When I differentiate e to the x, I get e to the x. And cosine becomes, the integral is sine, and the derivative is negative sine. So it really doesn't matter which one I say is u and which one I say is dv, because they're all going to have more or less the same philosophy coming into play. And what that same philosophy is to say, look, it's going to be roughly the same format, whether I integrate or differentiate. So let's pick. I like to say, let's make u be my e to the ax. I just like taking derivatives of e to the ax. And so the cosine bx dx, that's my dv. So du is going to be the derivative. The a comes down, e to the ax dx. V. Now, I have to take the antiderivative of cosine of bx. Now, the antiderivative of cosine is sine. That's not bad. How do I handle this bx? Well, the answer is I take the following. I divide by b. So it would be 1 over b sine of bx. All right. Now from here, we do the following. uv. So I have 1 over b e to the ax sine of bx minus the integral v du. So I can write that as a over b e to the ax sine of bx dx. All right, so we've made a little bit of progress, maybe, but we still have more or less the same kind of integral. And so now let's go ahead and we're going to do the same thing in the same substitution. So u is still going to be e to the ax. And here, this sine bx dx, I'm going to call that v. And this constant, I'm going to think about moving that outside. du, similar as before, is a e to the ax dx. And oops, that's dv. And so v, okay, now what's the integral sign? Integral sign? Negative cosine. So negative 1 over b cosine bx. All right, so we have 1 over b e to the ax sine of bx. And now we have minus this a over b times, all right, product rule. Sorry, not product rule. Integration by parts. So the product rule and integration by parts, they're more or less the same. See, it's easy to get confused. uv, and so that's going to be minus 1 over b e to the ax cosine bx. And then minus the integral v du. Now notice I have a minus already, so two minuses make a plus. Integral a over b e to the ax cosine bx dx. All right, now at this stage, if we multiply this through, we have 1 over b e to the ax sine of bx. Here I'm going to multiply that minus a through, so that's going to be plus a over b squared. So minus a over b times minus 1 over b, a over b squared, e to the ax cosine bx. And now here, this last term, minus a over b, and here I have plus a over b, so that's minus a squared over b squared times the integral e to the ax cosine bx dx. And now we say, we're back where we started. Except we're not. It's true that we still got to the integral e to the ax cosine bx. That still matches. But what's not true is, notice in front is a 1. Here it's minus a squared over b squared. Different, and different is good. And by that we mean we can do the following. Let's take that and move it to the other side. So I'm going to move this e to the ax cosine bx dx to the other side. And if I do that, I'm going to get 1 plus a squared over b squared times the integral e to the ax cosine bx dx is equal to, and now we have what's left, 1 over b e to the ax sine bx plus a over b squared e to the ax cosine bx, and plus c. Now where did the c come from? The c came from the same idea that we talked about when we had that crazy 0 equals 1 problem. These integrals aren't quite the same. They differ by a constant. So that's where my c comes from. Now I'm almost done. The last thing is just to make a couple of things to clean this up. Let's make a note and say this expression, if I add it up, makes it a squared plus b squared over b squared. And now what I'm going to do is I'm going to multiply both sides by the reciprocal, b squared over a squared plus b squared. And so multiplying everything by b squared over a squared plus b squared. So again, multiplying everything by a nice constant, b squared over b squared, a squared plus b squared. Okay, there we go. What do we get? Well, we get 1. So we get the integral e to the ax cosine bx dx equals. Now here, notice I have a 1 over b, and here I have a b. So I get to do a little bit of cancellation. So that becomes b over a squared plus b squared e to the ax sine of bx. My next term, there's a b squared downstairs, which completely cancels. So I'm left with a over a squared plus b squared, e to the ax cosine bx. And then I have c times a constant, but a constant times a constant is a constant. So I'll write it like that. And thus, we have found the antiderivative of e to the ax times cosine bx dx. And what did we do? Well, we set it up. We did integration by parts once and twice, and then we rearranged. All right. This is a nice and kind of useful trick, and we'll see things like this in the next lecture where we can use it to do what's called power reduction, where we can sort of get into a cycle and help simplify a couple of expressions. All right. So finally, last thing for today, today's last topic. Suppose I want to do the following. Find the volume when the region between 0 and pi for x and 0 for sine x for y is spun around the y-axis. That's a terrible looking y, but that's what that's supposed to say. Now, we did a problem like this on the quiz, and it was slightly different. So x goes between 0 and pi, y goes between 0 and sine x, which means our region is this part. It's what's underneath the sine curve from 0 to pi. Now, on the quiz, we did a revolution around the x-axis, and we got sine squared, and we say, aha, we can simplify sine squared. Easy, easy, easy. But now I want to do it around the y. So I want to go that way and revolve around the y-axis. So here, if we're given a function of x, thinking back, and I know it was a long time since Monday, but we can do it. We can do it. So if we take a very small strip, dx, and we spin it, what we're going to see is that we're going to form shells. So to find the volume, we use the shell method. All right, so the volume will be 2 pi integral a to b of two pieces. This is going to be our radius, and this is going to be our height. All right, so let's fill these pieces in. Our height, how high is this? It's sine. Sine. Our radius. Well, how far, if I'm at x, how far am I from the y-axis? I'm x. And of course, I should have said not a to b, it's 0 to pi. All right, now we couldn't have done this in the last chapter. We could have asked the question, but we would have had to stop here because we didn't know how to integrate something like x sine x. Now, we don't have to stop. We say, aha, this is the perfect kind of thing to do integration by parts. So let's write this integration by parts. What would we do? Well, we have two terms. One to differentiate one to integrate another. In this case, this is a great thing to differentiate, and integrating this doesn't really change anything. du would be dx, v would be integral of sine is negative cosine. Okay. So we get that this is equal to 2 pi times, well, uv minus x cosine x from 0 to pi minus the integral v du minus x plus cosine of x dx, and we're going from 0 to pi. Okay, so we have 2 pi. Now here I can evaluate. So I plug this in, I get minus pi times cosine of pi. which is cosine of pi, -1. Okay. Subtract, plug in 0, I get 0, plus integral of cosine is sine, and I'm going to evaluate from 0 to pi. Now, sine of pi is equal to 0. Sine of 0 is equal to 0. So this part actually drops out. That drops out. Minus pi times -1 is plus pi. So it's 2 pi times pi, which means 2 pi squared. Okay. 2 pi squared. Good. Good. So, okay, that's the product rule. Integration by parts rule. Comes from the product rule. Good rule to know, and we're going to use it quite a bit in the weeks to come. All right, that is it for this lecture, and in the next lecture we will continue techniques. All right.